Section 3.10, Linear Approximations and Differentials. The point of this section is as follows. It is sometimes difficult to calculate values of a function near x equal a. To simplify this, we can use the line that is tangent to the function at x equal a as an approximation of those values. This means we use the tangent line at a point a, f of a as an approximation to the curve y equal f of x when x is near a. Using the point slope form, y minus f of a equal f prime of a times x minus a, and solving for y, we end up with y equal to f of a plus f prime of a times x minus a. This form is called the linear approximation of f at a. We can also write that in function notation, swapping out the y with L of x, and then writing L of x equal f of a plus f prime of a times x minus a, and this is called the linearization of f at a. So for our first example, find the linearization of the function f of x equal to square root of x plus 3 at a equal 1, and then use it to approximate the numbers square root of 3.98 and square root of 4.05. Once we find those, we want to ask, are those approximations overestimates or underestimates? So first of all, for our linearization, we're going to need a few things. We'll need f of a, which in this case is f of 1, which means we'll plug in 1 to the square root of x plus 3. So that gives us f of 1 is the square root of 1 plus 3, or the square root of 4, which is 2. We'll also need the derivative. But before we find that derivative, maybe we should write f of x as x plus 3 to the 1/2 power. Then when we find the derivative, we're just going to use the power rule and the chain rule. This becomes 1/2 times x plus 3 to the negative 1/2 times the derivative with respect to x of x plus 3 by the chain rule. But the derivative with respect to x of x plus 3 is just 1, so f prime of x is just 1/2 times x plus 3 to the negative 1/2. And then finally, f prime of a is the next number that we're going to need. That's just the derivative evaluated at 1, which becomes 1/2 times 1 plus 3, or 4, to the negative 1/2, which is 1 over 2 times the square root of 4. That's just 1 over 2 times 2, which is 1 over 4. So putting this all together, L of x is f of a, which in this case is 2, plus f prime of a, which is 1/4. I'm going to write that as 0.25, times x minus a, so x minus 1. So that's our linearization of the function at a equal 1. Now let's use that to figure out the answers for those square roots. So first let's take a look at the square root of 3.98. How this relates to what we were just looking at is, let's think of the square root x plus 3. If you plug in 1 for x, we get the square root of 4. The square root of 4 should be pretty close to the square root of 3.98 because 4 and 3.98 are pretty close to each other. So the way that we can use our result is we're going to rewrite 3.98 as a number plus 3. And that number would have to be 0.98. So then this turns into just evaluating our function at 0.98. Which we can then approximate with our linearization evaluated at 0.98. Because again, we can use this for any values that are close to a, in this case close to 1. So L of 0.98 is 2 plus 0.25 times 0.98 minus 1, which is 2 plus 0.25 times negative 0.02, which is 2 minus 0.005, which is 1.995. So by the same logic, the square root of 4.05, that's just the square root of 1.05 plus 3. So that's f of 1.05, which we can approximate with L of 1.05. And L of 1.05, that's just 2 plus 0.25 times 1.05 minus 1, or 2 plus 0.25 times 0.05, which is 2 plus 0.0125, or 2.0125. Some historical context for what we just did. The square roots that we were trying to approximate, we know that there's an easy way we can find those now with a calculator. But calculators weren't around a couple of hundred years ago, but people were still interested in what were those square roots equal to. They know that those numbers inside are close to 4, so the answer should be something close to the square root of 4, which is 2. So what they used was a concept that's a few hundred years old, the derivative, and they found a way to approximate those by thinking of the tangent line approximates the curve. And what it turns out to give us are some calculations that are actually very easy to compute. Everything that I did with the L function just involves subtraction, multiplication, and addition. Very simple things to actually accomplish. And those approximations, if you do plug these into your calculator, like the square root of 3.98, you'll see that what you get is 1.994993734, which is pretty close to the answer that we got. And of course, this is an approximation in itself also. This would continue forever with these decimals. The other one that we got, the square root of 4.05, if you plug that into a calculator, you would get 2.01246,118. Again, very close to what we just got. From these square roots, we can see that the answers that we got are over approximations, or overestimates. We could have figured that out without grabbing a calculator also by just looking at a graph. I'm going to switch over to Desmos, and we can see the graph of our original function, square root of x plus 3, and then also the graph of the tangent line. So here, this purple graph is the graph of y equal to square root of x plus 3. And then if I plot the tangent line, y equal to 2 plus 0.25 times x minus 1, we can see that this line is above the purple graph. And in fact, it's above it at all times. Which means that if we're using the tangent line to approximate the curve, that's always going to give us an overestimate for this particular function. So now let's look at a new definition. If y equal to f of x is a differentiable function, then the differential dx is an independent variable, meaning it can assume any real number value. Then the differential dy can be defined as dy equal to f prime of x dx. So those are just two definitions, but I'm going to draw a picture similar to the one that we saw for the square root of x plus 3 to get a little bit of a better understanding of this. So I'm going to draw a curve that's concave down. So I'll start with that. So this is my curve y equal f of x. And I'm going to have a tangent line to the curve at a point P. So first I'm going to draw the point P here. And the point P has coordinates, as you can see below, x comma f of x. So here's P, x comma f of x. There's an x value associated with that on the horizontal axis. Before I draw the tangent line, I want another point on the curve called Q. And Q has coordinates x plus delta x, which means I started at x and I added a change in x and I reach a new x-coordinate, x plus delta x. And of course, to get the y value for q, you would just take that x value, x plus delta x, and plug it into your function. So that's why we have q with these coordinates. We're also going to notice that for delta x, we can just also call that dx by one of the definitions above. So then let's draw our tangent line. And again, that would be to this point P. And just like the graph that I had earlier, it's above my curve. And I'm going to draw a point on my tangent line that is above point Q. It has the same x-coordinate, x plus delta x. So now, let's first of all notice that delta y is just the change in y. So that would be the change in y values on the function, which would just be the y-coordinate for q, f of x plus delta x, minus the y-coordinate for p, f of x. This should remind you of the difference quotient we saw with derivatives. And then with our tangent line, the slope of the tangent line can be found with the derivative, f prime of x, which we can just think of as a slope like dy dx. So when we notice dy dx, now we can start thinking that relates to rise over run. The rise of this slope, the vertical distance dy, that would be demonstrated like this on the graph, because that's the change in the y values on the red tangent line. So first of all, right here, notice dy is a little bit longer than delta y. It's this over approximation. So the rise of this slope, the vertical distance dy, is simply the slope, dy dx, times the horizontal distance, dx. In other words, dy is the same thing as dy dx times dx. But that's just the same thing as f prime of x dx, which is the definition that we had. So finally, where delta y represents the actual amount that the curve y equal f of x rises or falls when x changes by an amount dx, the value dy represents the amount that the tangent line rises or falls, and is thus an approximation of delta y. So this is our summary of what we were just talking about. dy is an approximation of delta y. We saw this when we talked about marginal cost. What we were getting from our derivatives was an approximation of what was actually happening in reality. So as an example, let's compute delta y and dy for the given values of x and dx equal to delta x. Then sketch a diagram showing the line segments for dx, dy, and delta y. So here y is equal to x minus x cubed, x is equal to 0, and delta x is equal to negative 0.3. So first of all, we can notice that delta x being negative 0.3, that's also just our dx. Delta y would be our function evaluated at x plus delta x minus our function evaluated at x. In this case, x is 0 and delta x is negative 0.3. So plugging in 0 for x and negative 0.3 for delta x, that would give me, first of all, negative 0.3 minus negative 0.3 cubed. That's evaluating f of negative 0.3. And then minus f of 0, which would just be 0. Simplifying what we have, this gives us negative 0.3 minus negative 0.027, or negative 0.273. So that's delta y, the actual change in y values. To find dy, we need the derivative of f and then multiply that by dx. So first of all, the derivative of our function would be 1 minus 3x squared, and then we're going to multiply that by dx, but we need to evaluate x at 0 and dx at negative 0.3. So this turns into 1 minus 3 times 0 squared times negative 0.3, and that just ends up being negative 0.3. So this is our dy. One thing just to point out even right here, delta y, we had to cube negative 0.3. But with dy, all we really had was a 0 squared, very easy, and then we just had multiplication and some subtraction. That's it. So now let's put this all together into a sketch. So I've already drawn this in Desmos, and I'm going to bring that in, and then we can draw our line segments. So in our graph, we can see 0 for x right there, negative 0.3 for delta x. That would just be there. So this is dx or delta x. dy would be the change in y values. That was when we went down on the graph. And that gave us delta y. But then dy, notice that dy is negative 0.3. When compared to negative 0.273, that'll go a little bit further than what I just drew. So dy in red here goes beyond. And we already have that its value should be negative 0.3. So it would be down there. So this is dy. Notice here dy would be an under approximation because the tangent line would be under the curve at this point. All right, so finally to summarize this whole section, we can now put linearization and differentials together. The approximation dy for delta y becomes better as delta x becomes smaller. Also, dy is an easier computation than delta y. Just think of what we just noticed above. In the notation of differentials, the linear approximation that we had earlier can now be rewritten. F of a plus dx is approximately f of a plus dy. Because as f is evaluated at a plus dx, for small values of dx, then f prime of a times x minus a, that was the part in the linearization, that's really just approximated by dy. So for example, in our first example, we had f of x equal to the square root of x plus 3. And we could write dy equal to dx divided by 2 times the square root of x plus 3, just by rearranging our derivative. If we let a equal 1 and dx equal delta x equals 0.05, then dy is equal to 0.05 divided by 2 times the square root of 4, which ends up being 0.05 divided by 4, and that gives us 0.0125. Thus, the square root of 4.05 is really just f of 1 plus 0.05, which equals f of 1, that's our a value, 1, plus dy, which we saw was 2 plus 0.0125, giving us 2.0125, the answer that we had before. So here's another way of getting that same answer, but just by using differentials.